Okay, so I wanted to provide a short video presentation to ensure that all of my NET1001 students have the same starting point for doing Lab 1. So this is an introduction to the MARIE Machine Architecture Simulator. MARIE stands for Machine Architecture. That is really intuitive and easy. I know it's a corny name. It's a computer thing. MARIE is used by several universities as a way of teaching the fundamentals of computer architecture, and I've been using it in this program, I think, since I started here. MARIE was created by Linda Null and Julia Lobar for bundling with their textbook, The Essentials of Computer Organization and Architecture, from 2006. It's essentially a CPU architecture visualization tool that simulates a very basic implementation of what goes on inside each core of your CPU. This is only a 16-bit CPU, but it follows what we call an instruction set architecture. An instruction set architecture means that everything that you can do with the simulator, or everything you can do with the CPU, is dictated by a strict set of commands that are actually baked into, in this case, the virtual ALU, or the arithmetic logic unit. MARIE emulates the von Neumann architecture model, which includes a memory which is used to store both instructions and data, a CPU with a control unit to fetch and decode instructions, as well as an arithmetic logic unit that can execute instructions, including fetching data from an input source and writing that data to an output source. MARIE uses a 16-bit word length, that is 2 bytes, and allocates basically a heap of addressable memory. MARIE also employs 5 registers inside the CPU, which are used for fetching and decoding data, as well as storing the results of the operations. MARIE also includes a built-in code editor and assembler, which allows us to write, assemble, and load code into the simulator to run. And finally, there's also a separate emulator that actually gives you a different view. It's a separate tool that you can load your programs into, and it allows you to visualize the code as it travels through the system. So you can see what clock pulses do what, where data travels, how it's fetched, decoded, and all those sorts of things, which is really fascinating and allows us to actually see how this works. So I know that many people are more visual learners, so that tool is really helpful for them. We will be using a Java-based version of MARIE. So in our labs, we'll be setting up the version 1.3, and it will run with pretty much any Java runtime. So if you have the latest Java runtime on your system, or even a relatively recent one, you shouldn't have any problems running this. There are steps for setting up MARIE itself, and the lab will explain that, and there are plenty of examples online. I wanted to talk about a few of the components of this so that you understand how this works. So a register is memory. It's a small word-sized memory location in the CPU itself. It's the only memory that the CPU can work directly on. The control unit, or the CU, will fetch code and data into these registers. It'll decode the operation and then invoke the ALU to complete the operation, which will interact in some way with the accumulator. So the accumulator is really the most important register, as it is singular and is where the results of an ALU operation will be written. And it's often where data is expected to be when we write to the output. It's also where we want to load data into the accumulator and then act on it. The AC is exactly 1 word in size, 16-bit or 2 bytes. And that's typical for all modern CPUs, that the registers are exactly 1 word in length. So the control unit has 2 dedicated registers. The program counter, which is the address of the next instruction to be executed. When the CU runs it, fetches the word from memory at this address, placing the instruction into the instruction register. Well, actually, it's a little more complicated than that, as it always is. I'm trying to simplify things. Really what the CU does is it fetches the whole word into the memory access register. So it controls the flow. It says, oh, I have the program counter. It says, this is where we're going. We're going to go grab this, put it into the memory access register. And then it copies the word in its entirety into the instruction register and also places the last 12 bits into the memory buffer register. Whether it's going to use it or not, it places them in there. And then that can be used as from one of the operations as the address to where I'm going to either read from or write to in the memory. So you should note that that means we have only 12 bits to address every word in our memory. So we'll look at this again in the lecture, but I want you to see that while there's a lot going on inside of the CPU, it's a lot of very simple things. At its heart, the computer is an elegantly simple machine. But that is actually what makes it hard for us to program, because we, as humans, are used to thinking in levels of complexity, which we often don't even interrogate or question. We just do it. We just think that way. So when we run Marie, the program sets aside just over 4,000 words of memory for all of our code and data. Know that the input is restricted to an input box in the application, and output is limited to a single 2-byte word being displayed onto a built-in output window. In a more complex chip, the output can be directed to memory locations that are listened to by services that send data to devices like video cards, disk drives, etc. We only have 12 bits, as I've mentioned already. We only have 12 bits for each address because we reserve 4 bits for the operation code, or what we often refer to as the opcode. You can always see all 4,096 words of memory in the Marie interface, and this is dynamically updated as our code is executed. So note that the reason why we only have 12 bits for addressing is that each line of code, machine code, starts with 4 bits for the instruction or the opcode itself, and the rest of it is potentially a memory address. And we often would call this kind of configuration of memory the heap. There's other ways of organizing memory, but normally when we talk about the place where the memory is loaded into and executed from, it's the heap. Usually when you are learning assembly language or machine code, you need to know how the instructions are formed. Because we only have 4 bits for an opcode, that means that we can only have at most 16 instructions in our instruction set architecture. So the number of instructions we have available to us is limited to the size of the word for the instruction that is dedicated to the opcode. I'll go through the instructions next, and then we'll write a little code to run. Note that we use mnemonics in place of hex numbers for our instructions. This is why we use assembly language instead of writing in machine code. It's much easier to understand a command like subtract or add than it is to remember the numbers of 4 or 3. So as long as we can understand that when we go to look at memory dumps, that's where we'll see those numbers, and we'll be expected to know in that architecture how much is the opcode and then how much is the data, so we can look at it and parse out what's there. But this means that we are required to assemble the code into the bare number format, which is called machine code. So the assembly language is an intermediary step to allow us to write code in something that looks at least a little bit readable. When we have pre-made libraries, for instance, such as if we're linking with the operating systems, we can actually link our assembled code with those libraries. Okay, so I wanted to run through the various instructions really quickly. we're going to have some memory instructions to do with the accumulator. First, we have load x, where we will use the word load, and then we will give it a 12-bit address. And that's the address that we want to look at and load what are in those bits into the accumulator. Store is the opposite. We take what's in the accumulator and we load it into the address, which is interesting because in both of these cases we can load a whole word from those places because it's the address that's truncated. What's in the address is going to be a full word. And then oftentimes we need to clear the accumulator so that we can do other operations. So we have a command that allows us to store 0000 in the accumulator. One of the fun facts about working with Marie is that if you want to work with 1, I want to have a 1 for incrementing, I've got to create a 1. There is no 1. You have to create all of your constants as well. Input will accept a value from the keyboard, so there's a little dialog that we'll see where you can actually put in a number or a hex value or a character, I believe, and then it will accept that. You hit enter, it accepts it, and then it puts it into the accumulator. Output will put things onto a little screen, and you'll see that we have a little pull down that allows us to say, oh, we want the character representations of ASCII, or we want to make sure that there's no line feeds used, otherwise it'll just down the side of the screen, putting in a line feed after every character. So we can actually make that work a little bit like a terminal, although we can't, it's more of just an output terminal. Then we have some math instructions, and there are 3 that we have available to us. You can see there's no floating point unit. We're all in integers. This is pretty standard stuff. Although we should say that Marie is a machine that actually works with 2's complement number format, so we can work with negative and positive integers. Add x will add the value at address x, so whatever's in address x, to the accumulator, placing the result in that accumulator. So we also have subtract x, which will take the value at address x and it will subtract it from whatever's in the accumulator, and it'll put the result into the accumulator. We also have an indirect add, which allows us to use an address that we store in a memory address, so an address that points to an address, and that address that's inside it is used as the address to go and fetch the value that we're going to add to the accumulator. So this allows us to do things like have pointers that point to other places, and then we can manipulate those pointers to point to other places. We can add 1 to it to move along in an array, for instance. So this is the only way that we can actually do this, but it allows us to do indirect referencing. Marie also has control flow instructions, and every computer will do 2 things. It allows us to do some math or some working with the bits themselves, and then also it allows us to read. So we can write, perform operations, which is kind of a write operation, and then we can ask questions. So control flow is done by asking questions and controlling the flow through the program based on those questions. It's very simple. It only can read what's in the accumulator and make a decision based on if it's positive, negative, or 0. And what it can do is it can actually skip 1 instruction. So what I can do is I can put an instruction that says jump over here or jump back to the top of my loop, and then when I hit the end of it I run this skip condition, and the skip condition will say, oh yeah, I've hit the end of the loop, it's now 0, go to the next line after it, so it will not hit that jump. So the commands here are jump, which takes an address because everything is addressed, data and the instructions are all in there. And it'll actually take the address that's in X and it'll put it into the program counter. Again, X is referring to an address. We will put an address there. It's to be replaced. But when we go to run the next fetch and decode, it will actually look at the program counter and go there rather than what was in it when we started. This is why the program counter always points one instruction ahead. There are more complex architectures that do this a little differently, but this is pretty common. Skip condition will actually take a value after it, which looks like a 12-bit value. It's either 000, 400, or 800. So these are all hex numbers. These are the only options that are implemented in this version of Marie. So it will look at the accumulator and it will say, oh, is it a 0? Is it negative? Is it positive? And it will, if those things are true, the thing we're testing for is true, it will jump over the next or skip the next instruction. We also have some ability to build subroutines. And so we have a jump to subroutine, which will actually do it's a little more complex. So we probably won't be playing with this, but I want you to be aware of it. So basically what we're going to do is we're going to take the current program counter value and we're going to store it into whatever address we give it. So it's an address, it's going to hold basically an address. And then we place the x plus 1, or that address plus 1, so the next line after it, into the program counter, meaning that we have a subroutine that starts off with a place to hold the memory address of where we're going to be able to go back. And then we can, the next lines will start a new section of code. And when we're done, we'll use a jump I, which is an indirect jump I, which will actually reference the start again of our subroutine, which is where we stored our way back. So then it'll take that number, that PC, put it into that address and put it into the PC, and then jump me back to where I was in my program. So this is essentially how functions, subroutines, procedures, those things are all done in code. We're used to just saying, oh, go do this, go do that. We have to actually dictate everything and control what's going on in assembly language. The final command that's available to you in the Java version is halt, which you'll need at the end to stop. Otherwise, usually your data is after your program. Otherwise, it'll start trying to interpret your data as if it was code. So that's kind of embarrassing. You don't want to do that. The other thing that I will say that before we take a look at the code is normally we use an assembler directive to start. And we usually use the assembler directive that tells it where in memory do I start writing this code out. Because all the code gets loaded into memory and then it begins to work with the CPU. Usually the command is org and then it has to line up. So usually we put org 0100 or whatever the address is. So we'll actually create an org in our code just to make it clean. So that's it. 13 instructions. Let's play with them a bit and then I'll show you the visualizer. To install Marie, you simply need to extract the files into a folder. It'll be the Marie sim folder, and you're going to look for the .jar files. Those are Java runtime files. So they're executable, meaning they'll invoke the Java runtime engine and they will run in that. There are 3 here that you're going to be working with. Well, actually 2. You'll work with the Marie sim.jar. That's the primary tool, which we'll open. It'll look like this. Hopefully that's nice and clear. It's as clear as I can get it. We also have the data path tool, which we will look at in just a bit. But what we want to do is we want to look in Marie here. And I'm going to load in a file. Well, actually, we need to edit some code. And I have some code written just to save us some time. So this is the code editor and assembler. And you can open up your code. We're going to open up our hello world.mas, which is Marie assembler. This is Marie executable. This is intermediary files that are used for compilation process. So we're not going to worry about those so much. but this is the code. I'm going to pull this down just a bit so you can see it. And it's a very simple piece of code. Hello world is traditionally the first thing you program in any language. So whenever I learn a new language, the first thing I do is I bring it up in an editor and I write a hello world, and I see that I can actually get some output and that I can actually work with the language. So it tells me everything's set up correctly and that I'm going to be able to get some feedback. You'll notice a couple things about this code. So first off, these are typically your commands, but there are some of these commands are not opcodes. Org is going to say put this code in the very first position in memory, which is 0, 0, 0. I can put just 0 if I want because it's the same thing. And I've written comments on every line of code. And that is traditional for doing any kind of assembly language. It's a really simple line that tells me why I'm doing what I'm doing. The commenting strategy for assembly is like this because it's really not apparent what actually is happening in the code otherwise. And so I recommend that you adopt that strategy. It has an added benefit that when you are recoding a project for submission, that I can see you're demonstrating that you understand the code, which is what an academic has to measure. So when you're being measured in here, it's, you can get code from all over the place, but if you can't explain how that code works, then you can't get the marks for it. So the commands are load, string base. This would be like the X that we used. We're using the names. These are called labels. So you'll have labels refer to the address of whatever line they are associated with. So while is associated with the address of the load instruction. So you'll see that when I go down here and I jump back to the while loop, I'm jumping to the top. I'm jumping to that address. So this is going to move me around. I have a little bit of an indirect thing going on here because I'll walk through that code in a second. But down here I have my data section. That's traditional for assembly language programming to have a data section at the end. And note that I have, for the value 1, I have to actually have a constant somewhere. I have these iterate and index, which are going to change as I go along, and the string base is going to be the location of this first letter in memory. Well, how do I know that location? Well, 12 is hex, right? So it is 16 for 10, 17, 18. So starting from 0, it's the 18th, or it should be 19th line. If this is at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There we are. Perfect. So we're going to be starting our read here, and we're going to actually use that string base to create the index and move it along each time. This is the codes could be cleaned up a little bit, tightened up a little bit, but it'll do for our demonstration because it does the steps quite nicely. I don't like how that keeps getting rid of my lining. This is not a very nice editor to work with, but for what we're doing here, this will work. So when I'm done, I'm going to assemble my code. Well, actually, let's walk through the code first. And there is a cheat sheet here that gives you all the instructions and what they do. So these are all the ones that are available to you. If you're trying to code, it's under help. So here I'm going to put load, and I'm going to load whatever is in string base. So string base has a 12, so I'm going to load 12 into the accumulator. Then I'm going to add to the accumulator whatever value is in iterate. So there's a 0 here, so 12 plus 0 is 0. Then I'm going to store, because it's not, this is all in the accumulator, I'm going to store this into index. So index is going to be my offset or my address of the first letter that I want to print out. So you probably are wondering why I don't just print out the whole thing. Like, why can't I just put the word in? Well, in many languages you can, but in assembly language, we can only do one thing at a time. And so we only have 16 bits, we can process one ASCII character. So that's our limitations, and we have to program based on the limitations. So inside the language, we're going to then clear it out once we've figured out what this is and stored it out into memory. Then we're going to take the index and we're going to add it to, we're going to actually go and get what is at the address of the index and add it to the accumulator, which is why I cleared it out, because I want to be able to pull this 48 and put it right into the accumulator. And then I'm going to check and see if that number is a 0. And if it's a 0, then I'm done. I've hit this end, my null. And so I'm going to go to, if it's true, I'll go to the end, which means skip condition skips this line. And it goes here, and it just says end, which just halts the program. You have to put a halt in there. That's a non-negotiable. The org, if you don't put it in, will be a 0. But it is good to put it in. It's a good habit to be in. Makes your code cleaner. Otherwise, we skip to the do section. So the do section will do this and go back up to the while. So the first thing it does is it outputs what's in the accumulator. So notice that I didn't change the value in there, and by testing it doesn't erase the value. I'm able to use that value until I change something in the accumulator. This will always print out what's in the accumulator, which was the value at the address. Get the value at address. This should be get the value at address in index. There we go. From index. So there we go. And then we are going to iterate. This should be. Oh, come on. Index value equals 0. Yeah, why do I do this? I really like my code to look nice. Then I'm going to load in my iterator, and I'm going to add 1 to it, store it back in the iterator, and go back and get the next thing until I hit the null character. So this is a simple loop to print out a number of characters that are stored in memory. So let's take a look at what happens. When I assemble it, I can then go and look at the assembly listing. So you'll see on the left, this is all the computer has. But this is what it corresponds to, and it gives me all the code. Notice that org0 is not a command. All of these ones are actually commands because they're saying take up memory with these spots. But it ignores comments, it ignores extra space, and it lines it up fairly nicely here. But it assembles it, and it shows you this is what the code is that we're going to be able to work with. We're going to close that. You can print it from there. We can close this now. Yep. And then what I need to do is I need to load it into the editor. So I'm going to load in my hello world.mex, and you'll notice it stripped out all of the comments and all that good stuff because it's no longer there. But this is 0, and you'll see the green highlight says I'm doing what's in this address, and this is the address I'm working on, and this will move around as we go through the program. You'll also be able to look at what's in the accumulator, all of the different registers. You'll notice that the PC is 0 because that's what we set it to look at. We have an input which can take various different kinds of values. We have an output that can output various different kinds. We want to see it in ASCII. And we also want to set it to no line feeds so that it prints across. Otherwise, it'll print one letter on each line and add a line feed after each one. This just is a little output terminal. When I want to run through this code, I can say run, and it will run through the code fairly quickly. I can actually set a delay to make that shorter, but I'm not going to change that right now. But this printed out hello world quite nicely, moving through it. And when I'm done, I'm at this line. You'll notice that the PC is at 00E, which is right where it's pointing to. And so 00E would actually be up here. It's pointing ahead. But anyway, it's where I left off. When I want to run it again, you'll notice that it just goes right to the end, because it is already run and it has all these values have been changed as we went along. This is the whole of my code right in here. So in order to fix that, we just need to reload the code. So always reload your code before you run it. You can also step through the code, which will allow us to go through each line one at a time, and notice how all of the values keep changing. So this is very helpful for us if we're trying to figure out something goes wrong somewhere in our code. Well, what are the values at that point? Can we check that? So that gives us some debugging capacity, and then we can run. I believe it'll just continue from where it was, because these things do not reset unless I reset them. So I'm going to actually exit this and show you one more thing, and that is the data path visualizer. Again, I'm going to load in my code, and you can see I have all my code here as well, same as before. And I have up here a kind of a simulation of all the paths that go through for currents to actually go through. And it'll change these values. It'll change the bits in them. These are all roughly one word. Program counter and memory access register are both just the size of an address. So if we run and we can set the speed, you'll see that it starts to blink. It tells you exactly what it's doing. It has a fetch, decode, execute, fetch, decode, execute cycle that goes on. So for every clock pulse, it's really three things that happens: fetch, decode, execute, fetch, decode, execute. That'll come up later on in the course, but this allows us to go through, and we're not really seeing the output, but we are seeing what's happening here inside the program. So this is also very helpful for us. I'm going to close this off, and I'm going to exit, and we'll go back and I'll finish up the video with the slides. So I want to finish off and talk just momentarily about this visualizer, and I found that the data path visualizer in the JavaScript version is a little more robust. So this is a screen capture from that, and it'll show you things like you can see clearly all the lines and how everything is connected. But in order to use anything, there has to be ways that the data, which is a clock pulse, the clock pulse will be able to move through things and let the transistors do their work. That's all I really want to do to make sure that we're all on the same page. I'll let the lab itself give you some instructions as to what I would like you to do with Marie and what I'd like you to submit. Anything that I've covered off in here will be part of the quiz as well. So I've provided you a few extra links in case any of this is not clear. Hopefully this will help to set you up for success with Lab 5.